Yes,
computer?
hello everyone.
Okay.
I have a little bit of problem with my computer, so
So please note, I'll inform you at the right moment that where it is right, Paula is not Paula but Alexandra, because she was not able to connect by her computer.
It's my turn to present.
Not yet. Just 1 minute. We want to be just in time because we allowed people to have a 15 minutes break, and some of them could have a real coffee drinking, physical.
Okay.
I mean, I had just virtual coffee drink. Okay, so please allow me to open the second part of our program, the session dedicated to PhD students and fresh PhD holders. So I just want to tell you a few historical facts here also. At the beginning, the workshop was intended to have PhD students and their supervisors. So the supervisor were invited speakers, and PhD students had also the opportunity to attend these invited lectures and to give them also some of their results, to give some short presentations about their results in research. So in this session, we'll have one PhD holder and the others are PhD students. And because we are just sharp in time, I invite Alexandra Marchis to give her presentation. Please, Alexandra. Can you share the screen?
Yes, one moment.
Okay.
Please.
Okay, it's right.
It's okay?
Okay. Okay.
You can see it? My name is Alexandra Marchis. I have a little bit of problem with my computer, so Paula helped me with hers. I will present common fixed point theorems for enriched contraction in Banach spaces. We prove common fixed point theorems under an enriched type contraction condition for two single-valued mappings that are satisfying a weak commutativity condition in Banach spaces. We also prove that the unique common fixed point of these mappings can be approximated by means of Krasnoselski iteration, for which strong convergence is obtained. I began my search with the notion of commuting mappings. That was first.
I can't see your screen.
I didn't understand.
Sorry.
Are you sharing your screen?
Yes, we can see the screen.
Oh.
It's someone else who cannot see the screen? No, it's a problem with your computer in that case.
Okay, let me join again.
Can I continue then?
Yes, please.
Okay. I start my search with the notion of commuting mappings, a notion first introduced by Gerald Young in the article Commuting Maps and Fixed Points in 1976. There we have the notion fjx equals jfx. And here is the original theorem introduced by Young with commuting mappings. Having a result, f and g have a unique fixed point, common fixed point. A various type of weaker condition appeared The next one was weakly commuting mappings, introduced for the first time by Salvatore Sessa in the article on a weak commutativity condition of mapping in fixed point consideration in 1982. That states fjx minus jfx is smaller or equal than fx minus jx. Of course, this is just the beginning. In the next years, appeared another condition, weaker condition of commutativity. The next one was compatible mappings introduced by Young in compatible mappings and common fixed point in 1986. But in the same year, Tivari and Singh introduced the notion asymptotically commuting, which is basically the same thing. So we have two mappings, F and J, two self-mappings that have a limit when n goes to n from fjxn minus jfxn equals 0 whenever xn is a sequence in x such that the limit when n goes to n from fxn is equal with the limit when n goes to n jxn, and it equals t for some t in x. Of course, the list goes on. I stopped here from my article, but in the future, I am planning to work with some other weaker forms. I think everybody knows Picard-Banach contraction condition. Of course, it's a starting point for lots of articles. One of those is the notion of enriched contraction that was presented for the first time in the article Approximated Fixed Point of Enriched Contraction in Banach Spaces, made by Berinde and Păcurar in 2020, that states a mapping F, self-mapping F, is called an enriched contraction if there exists B in 0 n-style and theta in 0 b plus 1 such that the previous condition is assured. B x minus I plus fx minus fi smaller or equal than theta x minus I. Using a weaker form of commutativity with the notion of enriched contraction, I have proved two common fixed point theorems in which I have, as you can see, my first main result, two self-mappings, F and J, for which we have the condition B minus x minus I plus fx minus fi smaller or equal than theta ji minus jx minus ji. If the following conditions are satisfied, f lambda and j are weakly commuting mappings where f lambda is 1 minus lambda x plus lambda fx and g is a continuous mapping, then f and g have a common fixed point. I write A this time, and there is a lambda in 0, 1, so that the iterative method jxn plus 1 given by 1 minus lambda xn plus lambda fxn converges strongly to A. To support my theorem, I have an example. Let x be 1 over 2 to 2, be endowed with the usually norm, and f and j be two self-mappings define fx equals 2 minus 3x, and jx 2x over 3, x plus 1, multiplied with x plus 1. For all x in x, we define b and theta, and we start our work. we see that F is non-expansive, so it's clear that it's not a contraction. Next, we verify Young's contraction condition, and we reached out a contradiction. 9/4 is smaller or equal than C, smaller than 1, which is definitely not true. On the other hand, if we verify enriched contraction condition, we see that B minus 3 is smaller than 4B plus 4 over 3. So for any B in 5/7 nth and theta in 5/7 B plus 1, the inequality above holds. Next, we need F lambda to verify the commutativity condition, because we made our condition between F lambda and J. They are weakly commuting mappings. So I took B to be 1 and lambda 1/2, and I have F lambda 1 minus x. The first condition, first we verify commutativity condition, and we see that F lambda Jx is not equal with J F lambda x. So F lambda and J are not commuting mappings. So we verify weakly commuting condition, and we see that F lambda Jx minus J F lambda x is smaller or equal than F lambda x minus Jx. So F lambda and J are weakly commuting mappings. And we reach out the conclusion that the fixed point of F and G is 1/2. My second fixed point theorem is similar to the first, but I changed condition A with condition A1, in which F lambda and J are compatible mappings this time. Lambda is the same, 1 minus lambda x plus lambda fx. J is a continuous mapping, and we reached out the conclusion that T is the fixed point of F and G, and there exists an iterative map of Jxn that converges strongly to T. Of course, I have an example to support this theorem as well. This time x is minus 1/2 to nth die, in that with the usually norm, and F and G, two self-mappings defined on x. Fx is 6x to the power 2 minus x, and Jx is 4x to the power 2 for all x in x. We also define b in 3/5 nth die and theta in 3/5 b plus 1. We see that f in this example is not a contraction, because it would be a contraction if f would be a contraction, then 7 will be smaller than c, smaller or equal than c, and smaller than what? Than 1, which is definitely a contradiction. Next, we verify Young's contraction condition, and we reached out another contradiction, 7/4 smaller or equal than c, smaller than 1. Last but not least, we verify the enriched contraction condition, in which we, for x different from I, we reach out the inequality. B minus 7 is smaller than b plus 4. So for every b in 3/5 nth die and theta in 3/5 b plus 1, the inequality above holds. If we take, for example, b equals 1 and theta equals 2, we obtain 6 smaller or equal than 8, which we all know is true. Next, to verify commutativity condition, we need f lambda x, which in this case for b equals 1 and lambda equals 1/2 is 3x to the power 2. We verify every condition in turn. First,
2 minutes remaining.
Yes, I'm almost done. We see that f lambda jx is not equal with j f lambda x, so there are not commuting mappings. We verify weakly commutativity condition, and we see that 12x to the power 4 is bigger than x to the power 2, so definitely are not weakly commuting. But the limit when x go to 0 from f lambda x minus jx is 0. That implies that the limit when x goes to 0 from f lambda jx minus j f lambda x is 0. So f lambda and j are compatible mappings, and the fixed point for f and g is 0. Conclusion. We introduce a common fixed point for enriched contraction, this time for 2 single-valued mappings that satisfy a weak commutativity condition. The notion of enriched contraction was introduced for 1 single-valued in the article Enriched Banach contraction. We showed that the unique fixed point can be approximated with Krasnoselski iteration, and we showed relevant examples to see the difference between weak commutativity condition used in this paper. In the future, I am planning to prove common fixed point theorem in which condition A is replaced with a weaker form, and even make fixed point theorems for hybrid pair of mappings. This is my biography. Thank you for your attention.
Thank you, Alexandra. You were sharp in time, exactly 15 minutes. So I congratulate you. I thank you for this nice presentation. We can afford a few comments, questions coming from any side, professors or PhD students, please. Yes, please. Cancel the sharing.
I have no idea how.
You have to go there to.
Here.
Where is the?
Stop sharing.
Acolo trebuie să mergi. Okay, now it's fine. So.
Can I ask some question, Professor Beringer?
Not to me, to Alexandra, I suppose. Yes, of course, please.
Okay. Thank you for a very nice talk. Okay. Now I and my student interested in this topic related to enriched contraction. Okay. In your work, you study about the commutative commuting condition on F lambda and G. That right?
Yes.
Your result. Okay. Okay. How about if we you assume the commuting condition or some condition on F lambda and G. That right?
Yes.
Okay. How about in the case of the commuting property on F and G directly to F?
I am planning in the future to do this commutativity condition on F and G. This time was on F lambda and G. Of course, it's more easier, but planning in the future to make between F and G.
Okay.
Thank you.
Thank you.
Thank you for the question and for answer. Very, very pertinent question. This is true. It will be more natural to have this condition about F and G, not about F lambda and G. Okay, this is for technical reasons. Any other questions, remarks, comments? No, thank you very much, Alexandra.